All right, this next theorem, the alternating series estimation theorem, is a useful theorem for it provides a way of estimating any convergent alternating series to a specified degree of accuracy. The alternating series estimation theorem tells us that if you have a convergent alternating series, then the true sum is this value S. That's the true sum. It's the value to which this series converges. Then S sub n is just the nth partial sum. So the absolute values of this difference tells us the size of the error. So what's the difference between the true sum and our estimation, sum nth partial sum? The absolute values just mean we're not going to consider which one's greater than the other one. We're just going to look at how far apart they are. What's the distance away they are from one another? So this distance, the size of the error, is the size of that first omitted term. So for example, if I have the, let's say here's a convergent alternating series. 1 minus a half plus a third minus a fifth plus a seventh, so on and so forth. It's a terrible 7. That is a convergent alternating series. It just so happens to converge to the value natural log of 2, which I believe is about 0.692. I could be wrong, but I think that is it, as I throw a calculator on the floor. 693. Okay, 693, if we round to 3 decimal places. Okay. Let's write a few more out. 1471806. Okay. So this is an alternating series. So what I can do here is, for instance, the third partial sum. Right? If I write this out as a series, this is, or in series notation, negative 1 to the n over n. Oop, I guess this should be n plus 1. We want the first term to be positive. Yep, that works out. So the nth partial sum here, S sub 3, would be 1 minus a half plus a third. So if we get a expression for that, we have 5/6, which as a decimal is 0.833, actually just 3 repeating, 0.83 repeating. So now this alternating series estimation theorem tells us that the true value, which is natural log of 2, minus this value, 5/6, should be, I'm going to say less than, but a should above it because it's the theorem's result. It should be less than, or it should be strictly less than the first term that we omitted. Well, the first term that we omitted is this 1/5. Notice here that the b sub n, this is just the positive terms. The actual alternating bit, the piece that determines what the sign's going to be in front, is not included in b sub n. It's part of this negative 1 to the n minus 1 bit. So this b sub n plus 1 in our case is not negative 1/5. It's just the positive 1/5. So this should be less than 1/5. Should be. So let's actually take a look at the value of this. The natural log of 2 minus 5/6 is an absolute value. This is 0.1401861528. And of course 1/5 as a decimal is 0.2. So this does check out. This is definitely less than 0.2. But the neat thing is this isn't just coincidence or happenstance. This will always work out. So no matter how far you go, no matter how accurate of a partial sum, you will just grab that next term that you forgot, and that is an upper bound to the size of the error.